In the last lecture, we started talking about projective representations, or, as is more colloquially known, representations up to a phase. This is a representation of a symmetry group with elements t, t bar, etc., for which the corresponding operators which act on a Hilbert space, u of t bar, and so on, obey the following condition. U of t times u of t bar is e to the power I phi t comma t bar times u of t bar. If this phi had been 0, then we would have had a standard or genuine representation, or a non-projective representation. The presence of this extra phase phi makes things a bit different, and in quantum mechanics, such projective representations can of course be present, and not only that, can have important physical consequences. Now, we have also seen in the last lecture that this particular phase function phi, which depends on both of the two symmetry operations t and t bar, which enter into the composition rule here, if it belonged to something called the trivial 2 cocycle, or in other words, if there existed a function of a single argument alpha, so that phi of t comma t bar were actually equal to alpha of t bar minus alpha of t minus alpha of t bar, then this phase vector can actually be eliminated by simply redefining the phases associated with each and every one of these unitary operators. So the question that we had asked near the end of the last lecture was the following. Is it possible to give a criterion which will establish whether a given group has no intrinsically projective representations, that is, whether all projective representations of a given group are really of this kind described right now, where you can get rid of this extra phase factor simply by redefining the phases of the individual unitary operators. Now, we have seen that a consequence of this projective representation is that the generators of the representation obey a commutation relation in which, in addition to having linear combination of the generators themselves, you also have additional terms which commute with each and every one of the generators. These are the so-called central charges. Now, the theorem that we are mentioning essentially says two things. If we can get rid of these central charges by simply redefining, actually shifting the generators by some real numbers, and if the parameter space of the group happens to be simply connected, then each and every one of the projective representations which this group has will actually be trivially projective, that is, will have phase factors which belong to the trivial 2 cocycle, and they can always be reduced to standard non-projective representations by redefining the phases. So, if a group has to have a projective representation for which the phase cannot be eliminated by this method, you need to satisfy at least one of these 2 points. Either it should be impossible to get rid of the central charges by redefining the operators, or the parameter space may be multiply connected. Now, in today's lecture, I am going to try to give a proof of this particular theorem. The proof will involve ideas from Lie group theory and also ideas from algebraic topology. I will try to state this in a way that can be followed by people who have not had a lot of exposure to these topics before. Our proof will be a proof by construction. That is, we will provide a recipe for constructing these operators u of theta vector, which is my shorthand for u corresponding to t of theta vector. Let me just point out that the vector sign on top of the theta is basically my way of telling you that there may be multiple parameters theta involved in describing an element of the Lie group. Now, from basic Lie group theory, we know this, that if you have 2 such symmetry operations T of theta and T of theta bar, their product will have a set of parameters which can be found out by evaluating a function of theta and theta bar, and this function has to be a smooth function. Essentially, the entire structure of the Lie group is encoded within the function's form. Now, what we demand here is that we will be able to construct u of theta which will satisfy the non-projective representation formula, that is u of theta bar u of theta will be u of f of theta bar comma theta. Now, in order to do this, what we are going to do is we are going to essentially think of paths in the parameter space, in the space in which the parameters describing a Lie group reside, and evaluate u of theta by solving a differential equation which tells you how these u of thetas change as you move slightly along the path. So a major ingredient here would be to figure out exactly how u of theta would change when the thetas change. And the answer to that can be easily seen from this equation itself. Note that if you choose theta bar to be infinitesimally small, that is, replace it by delta theta bar, where delta theta bar have components which are all infinitesimally small, then our basic composition rule becomes u of delta theta bar u of theta equals u of f of delta theta bar comma theta. Now, let us tackle the question about how u changes with theta in two steps. First, we have to figure out what this expression f of delta theta bar comma theta really is, but that's pretty straightforward. If we look at the eighth component of f, fa at delta theta bar comma theta will simply be fa at 0 comma theta plus the change which fa suffers because the first argument, the left hand argument, changes from 0 to delta theta bar. Of course, there are multiple components in delta theta bar, so this becomes, from the standard rule for partial derivatives, del fa del theta bar b evaluated at theta bar equal to 0, the value from which theta bar is changing, times delta theta bar b, plus higher order terms. This, of course, is nothing but a Taylor series expansion in the components of theta bar, and we have retained only up to the linear power. So now, for the basic theory of Lie groups, we know that if one of the parameters is 0, the null vector actually, then it really stands for the identity, which means the parameter for the composition will stay the same, and therefore fa0 comma theta is nothing but theta a. Now we will need to use this and actually a related set of numbers pretty often, so we give this a name. This quantity, of course, depends only on theta because it's being evaluated at theta bar equal to 0, and we call this h bar a, b, theta. It depends on a and b, of course. So these are like the eighth row, bth column element of a matrix which you can build out of all the a's and all the b's. Since a's and b's can take r values for an r-dimensional Lie algebra, this really forms an r by r matrix times delta theta bar b, of course. So on the right hand side here, we have u whose argument essentially is theta plus an additional piece, let's call that delta theta, and the eighth component of this delta theta is given by h bar ab, which depends on theta, times delta theta bar b. So, since delta theta bar b is tiny, we expect this to be a small change from theta, and therefore you can write the right hand side as u of theta plus del u del theta A times delta theta A plus higher order terms. But in all that is going to go on today, we are going to retain up to linear order in these small changes, so the higher order terms can be safely ignored. Now with this background, what you can do is write down the expression here, which is essentially the combination law for non-projective representations in the special case where theta bar is infinitesimal. And what we get is the following. On the right hand side, you have u of theta vector, this one, plus del u del theta A times the eighth component of delta theta, which is of course h bar AB delta theta bar B. So that's what we have written down here. On the left, on the other hand, what we have is basically the defining property for generators. When delta theta bar is tiny, you can always write the corresponding unitary operator as identity plus I times the generator TA, the eighth generator, times delta theta bar A plus higher order terms again. Now, if you just expand this out and compare the linear terms on both sides, you end up with del u del theta A h bar AB theta delta theta bar B on the right, and you get TA delta theta bar A times u theta on the left. In order to compare the two sides, you have to change the dummy index here, that is A, to anything else, in particular to B, which is the same value for the index on the other side. And then you can easily compare and see that you end up with the result that ITB u theta vector is del u del theta A, h bar AB theta vector. So the rate at which u changes when you change eighth component of its argument, del u del theta A, can be figured out from here. Of course, what you have here is del u del theta A multiplied by components of a matrix h bar with eighth row, bth column element of a matrix, and so on. So we should be able to solve this for del u del theta A provided that this matrix is invertible. In fact, the fact that this matrix is invertible essentially follows from the fact that inverses for every Lie group element exists, and you have to make use of the inverse function theorem of mathematics in order to establish that. I'm going to assume that you already know how to do that. In any case, it's pretty easy to see that if the inverse exists, and what we are going to do is call this inverse h. Of course, that is why we call the original set of derivatives h bar. So H is a new matrix whose BCth element when contracted with h bar AB and of course summed over B gives you h bar H as ACth element, and since we have said that H is the inverse of h bar, this is nothing but delta AC. By using this, can immediately write down that del u del theta's bth component is nothing but ITA HAB of theta. And this is a result that we are going to need to set up the differential equation, which will help us to figure out u of theta. Before we do that, let us establish a few properties of these matrices HAB and H bar AB, which are going to be useful in what is going to come. Let me remind you that for a Lie group, the function f, when you expand it in terms of the parameter components, has to have the following form. Fa must begin with theta bar A plus theta A. Those are going to be the only pure terms in theta or theta bar, and all other terms would have to be mixed. This, of course, is because you want to insist that if either theta or theta bar is 0, f must be the eighth component of the other parameter. What is important is this quadratic term, which must be of the form FABC theta bar B theta C. As we have seen before several times, this particular coefficient plays an immense role in the theory of Lie groups. Now, it's easy to see by a direct differentiation that the ABth component of the matrix H bar has to be of the form delta AB. That's simply the derivative of theta bar A with respect to theta bar B, plus a linear term, linear in theta that is, FABC theta C, plus possible higher order terms. Now HAB are components of matrices of a matrix which is inverse of H bar. And it's very easy to see that HAB, when you expand it out in powers of theta, must be delta AB minus FABC theta C plus higher order terms. In case you have never seen this done before, let me just show how to do this quickly. All you have to do is start by assuming an expansion of HAB theta. There will be a constant term, let's call that CAB. There will be a term linear in theta and higher order terms, of course. So the linear term in theta will depend, of course, on A and B and which Cth component you're talking about. So let's call that DABC theta C plus higher order terms. Now since HAB times H bar BC is going to be delta AC, what you have here is CAB plus DABC theta C contracted with delta BC, that's H bar BC's constant term, plus FBCD theta D. Of course, there are higher order terms as well. Now, these two together gives you a constant term of C AC, that's CAB times delta BC, and that immediately tells us that CAC must be delta AC. Then, what about the linear term? If you contract this, you get the linear term of D A CD theta D. You have to play a bit with index gymnastics here, that is, avoid confusing this free index C on this side with the dummy index C here, so which you have to change to D perhaps. And of course not confuse that D with this letter D here. Plus FBCD times CAB, which we have already established is delta AB, times theta D, and then just from the linear term you will be able to show that FABC must be negative of DABC. So this is what you will have here. Now what is going to be very useful for us later on are the results that H bar AB at 0, when the parameter theta is 0, is simply delta AB. In fact, there is also HAB at 0, that's pretty easy to understand. And the derivative of H bar AB of course depends on theta vector, that is, on the R component of theta. So, derivative of H bar AB with respect to theta C, which we write in shorthand as H bar AB comma C, at theta equal to 0 is simply FABC, the constants which make up the composition rule. And HAB comma C at 0 is given by minus FABC. This is a result which will be pretty useful later on. Let us now return to the task of setting up the differential equation whose solution will help us construct our U for various parameter values theta. Now, what we are going to do is set up standard paths in parameter space. In case the term parameter space seems a bit foreign to you, let me just point out that it's nothing but the fact that all the parameters which describe group elements, when you put them together, the set of such parameters, they form a set on which you can essentially introduce coordinates by looking at small enough patches. And these coordinates are nothing but these parameter values. So, basically it's a set on which you can do calculus by pretending that locally it looks like the set of real numbers or the R-dimensional real number space. capital R to the R. Now, what we are going to do is we are going to start by laying down standard paths in group parameter space. The paths are going to be called capital theta, and they will have, they are vector valued paths in the sense that for each point in the path you have these R components for the parameters given, and each parameter set is labeled here, each path is labeled by a vector alpha in parameter space, and it's a path, that means it's a map from an interval from 0 to 1 onto the parameter space. So basically what this does is simply this. It starts from the origin of the parameter space, which remember stands for the identity in terms of group element, and goes to the point where you have the components of alpha. That is, theta alpha at 0 is the null vector and theta alpha at 1 is the vector alpha. You have a continuous map. It changes continuously as S changes. So basically, as you progress along the path, the parameters describing a group element will continuously change, and hence the corresponding group element will also change continuously, and our U will change continuously. Our aim is to ensure that by the time we get to the end of the path, that is, get to the point alpha, the U has evolved from its value at U of 0, namely identity, to the value U of alpha. And in order to do that, you have to set up the differential equation which U alpha obeys along the path, and that's pretty straightforward given what we have already figured out. The path is parameterized by this single real parameter S, but as S changes, each and every one of the parameters change continuously. And if you want to figure out the rate at which U alpha S, this function which we define along the path, changes with S, is the following. dds of U alpha S is simply I times T alpha U alpha S HAB at theta alpha S, which, if you recognize, is nothing but the rate at which U alpha should change if it were obeying our composition rule with respect to theta B at the point theta given by theta alpha S. So, if you look at the picture here, all we are saying is as you move along this segment of the real line, as S changes, each S maps onto a point in the parameter space, which is the region bounded schematically by this purple curve here. And as S changes from 0 to 1, you trace out a bunch of points on the parameter space. You start from the origin and end up at alpha. At any given S, you end up at theta alpha S. And this really tells us that when you change S to S plus ds, go to a nearby point, of course, that will map onto a nearby point in the path. And when you go from this point to this point on the path, the rate at which the components of theta change are here. And that when you multiply it by the rate at which U changes, then those components change and add up for each and every one of the components. That's why you have a sum over B here. You end up figuring out exactly how much U will change when S changes from S to S plus ds. So this is a perfectly good differential equation. Of course, you have to remember that TA is an operator. So is U alpha. So this is an operator valued differential equation. A first order differential equation. And it has a rather obvious initial condition. You have to start at 0 with U alpha at the identity. So basically, what you're doing is, you have set up a path here, and you're going to solve this equation, which tells you how much U alpha changes as you move along the path. And by the time you end up here, you should hopefully end up at, okay, this is a hope at this stage, that where you end up with should be U alpha 1, but that's obvious, but it should really be U at the parameter value alpha. This is what we hope. At this stage, we hope this, and what we hope to do is to ensure that if we define u of alpha in this manner, this u alpha is going to obey the group composition rule. U alpha, u beta is u of f of alpha comma beta. Now you might say that's sort of obvious because that's exactly how we defined this differential equation in the first place. But actually that's not really true. What we did was to show that if the composition rule is obeyed, then you must change according to this differential equation. What we now need to show is that if u is a solution to this differential equation, it is actually going to obey the composition rule. U of alpha, u of beta is u of f of alpha comma beta. Now, as it will turn out, this is not really a very trivial thing to show. We will start out by trying to go to the point f of alpha comma beta using this path that we have already laid down as a part of it. So let me just first show you the picture corresponding to this, and then I'm going to try to describe what's going on here. Here we have the parameter space again. But in addition to the original point alpha, and of course the origin, we have two more points which have been labeled. Another point in parameter space beta, and the point which denotes f of beta comma alpha, which is the point here. And these three lines that we have drawn here, the green one, the orange one, and the blue one, the dark blue one, are actually the standard paths which we have somewhat arbitrarily set up, starting from the origin and going to the points alpha, f of beta comma alpha, and beta respectively. So, if you were to progress along this path using the differential equation that we had just written down, you would end up at u alpha of 1, which we hope to be able to set equal to u of alpha. If you were to progress along the dark blue path, at the end you would land up at u beta 1, provided of course you use the differential equation corresponding to that particular path. And similarly, if you used the differential equation corresponding to this path theta of f beta comma alpha of s, you would actually land up at u of f of beta comma alpha at 1. Now what we are going to consider is a different path, a new path, which is not actually a standard path, but which goes from the origin to this point f of beta comma alpha. Now it goes to this point by using first the original path that we talked about, and then a light blue path to get here. Now, here what we are doing is the following. S goes from 0 to 1, and by the time S goes from 0 to 1, you have to reach from the point 0 vector, that the origin, to this point. But how do you do that? You first travel along the path theta alpha, but you have to make it in half the time, so to get there at s equal to half. So basically you travel it twice as fast. So this is basically theta alpha at 2s for each value of the s. So this theta curly p of s is theta alpha at 2s when s is between 0 and half. In the next half, you have to travel this blue path. Now, the way in which this blue path is defined may look slightly complicated at the beginning, but let me break it up for you. Note that the point alpha, where you have reached at the middle of this new path curly p, can also be written down as f of the null vector, comma, alpha. And at the end of the path, you are supposed to be at f of beta, comma, alpha. So just imagine that as s evolves from half to 1, you are actually traversing, or not here, but there's an auxiliary point which is traversing this standard path from 0 to beta. Only it is doing that twice as fast. So, for some value of s, say half plus 0.1, it would have traveled 0.2, say maybe somewhere here. That gives us a parameter value on this path, and the corresponding value here will be f of that parameter value, comma alpha. As s goes from half to 1, remember you are starting out here and going twice as fast. That's why you are using twice as minus 1 as a parameter for this path which ends at beta. So that at s equal to half, you are at the origin right here, and at s equal to 1, you are at theta beta 1, which is of course at beta. And as you traverse this path, composing that particular value of the parameter using f with alpha makes you traverse this sky blue path here, so that at s equal to 1, you are at this particular point. So our description for theta curly p of s is, of course, for 0 less than equal to s less than equal to half, you just have the standard path theta alpha traversed twice as fast, and this slightly more complicated description. For the next half, when s is between half and 1, you have to actually traverse this path twice as fast, starting from s equal to half, and compose whatever parameter value you get along this path with alpha using f to end up with this blue path. So it's obvious that our new path curly p starts at s equal to 0 at the origin, right here. At s equal to half, it's at the end of the theta alpha path, which that means it's at the alpha vector, and at 1, it has managed to get to f of beta comma alpha. So the question that we have now is, if we try solving a differential equation to get u along this path, let's call that u curly p of s, then will this u curly p of s at s equal to 1 satisfy the group composition rule? And let us try to see whether that is true. The differential equation that u will satisfy along this path is of course the same, at least has the same form as the one we have seen so far. dds of u curly p of s is I times ta times u curly p of s. Then you have to take HAB, but HAB at the corresponding point on this path, that is at theta p of s. Then you have to differentiate theta p's bth component with respect to s and multiply by that. And that's your differential equation. So let's break up this differential equation into pieces. When s is between 0 to half, that's the easy part, the first piece. du curly p ds will simply satisfy I ta u curly p s HAB at the corresponding value of theta, which is theta along the standard path ending at alpha, but at 2s. And of course you take the derivative d theta b along the standard path alpha at 2s. Now if you look at it, it should be obvious that this is exactly the same differential equation that u alpha at 2s would also be. And what is more, the initial condition for both of these happen to be the same. When s is 0, u alpha at twice s is simply u alpha at 0, and that's of course the identity. And of course u curly p 0, we are going to start at the identity 2. And that means that at least all over the first half of this path, that is all over this green line, u curly p at s must be equal to u alpha at 2s. After all, you are satisfying the same first order differential. After all, these two functions satisfy the same first order differential equation and have the same initial condition. In particular, what is very important for us is that at the end of this half, when s equals half and you are at the midpoint of this path curly p, you actually have reached the end of the very first path, and therefore u curly p at half is exactly equal to u alpha of 1. What about the next half? That's going to be slightly more complicated, but will follow along the same lines. For s between half and 1, the differential equation is exactly the same, but it looks a bit more complicated simply because what you have to do is multiply ITA times U curly P at S by the value of HAB, but value of HAB at this particular set of parameters, and that set is f of theta b twice s minus 1 comma alpha. And of course the corresponding dth component of the parameter value is dfb, again at theta beta of twice s minus 1 comma alpha. So this is essentially exactly the same equation, except that it looks a bit more complicated because the parameter theta is a more complicated function of s here. So now, if we were to rewrite this dfb's using simple chain rule for partial derivatives, notice that it depends on s only through the first argument. So basically what you will do is you will differentiate with respect to the first argument, let's call that theta 2 here. So del fb del theta 2c of the function of theta 2 comma theta 1, evaluated that of course at theta 2 given by this quantity and theta 1 given by alpha, and then you multiply it by d of theta beta's cth component at twice s minus 1. So here once again you get exactly what you would get if you were to traverse the standard path from the origin to beta, but going twice as fast, starting at s equal to half and landing up at beta at s equal to 1. The important question that we have to answer is exactly what is this combination. And this is where we have to go back to our basic theory of Lie algebras and try to figure out exactly what this kind of a combination would simplify to. To see this, what we need to do is go back to group associativity property. Of course, the associativity property here just says fa at theta 3, comma, f of theta 2, comma, theta 1. This of course corresponds to t theta 3 times t theta 2, t theta 1. That must be equal to t theta 3, comma, t theta 2, comma, t theta 1. And that leads to this particular equation. Now, if we were to differentiate both sides of this equation with respect to the cth component of theta 3, partially of course, and then put theta 3 equal to 0, on the left hand side you would simply get h bar ac, because that's exactly how h bar ac is defined. You differentiate fa with respect to the cth component of the first argument and set the first argument to 0 after that. So this is just simply h bar ac at the second argument, f of theta 2, comma, theta 1. The right hand side of course is slightly more complicated because what you are now doing is you are evaluating the partial derivative with respect to theta 3c, but fa depends on theta 3c only because the first argument here depends on theta 3c through this combination. So you have to do del fa, del first argument, of course if you write this as theta 2, theta, comma, theta 1, the first argument is theta 2. So del theta 2b times the derivative of this quantity with respect to theta 3c at, of course, the beta component of that, that's the chain rule, and at theta 3 equal to 0. So this gives you h bar bc at theta 2. Now this can be rewritten using the fact that h and h bar are inverse matrices in the following form. The partial derivative of the function fa at theta 2b evaluated at an arbitrary theta 2, comma, theta 1 times hca at f of theta 2, comma, theta 1 is hcb of theta 2. Now this essentially tells you something very, very important. Notice that here you are evaluating the partial derivative with respect to theta 2b at an arbitrary point, some value of theta 2. But these are essentially the same kind of derivatives but evaluated at the first argument equal to 0. So these are also derivatives with respect to the first argument. This one, remember, is simply del fa del theta 3c of theta 3 theta 2 and evaluated at theta 3 equal to the null vector. So derivatives at the origin can tell you what the derivative everywhere is. So this is essentially the Lie group structure showing up. What happens close to the origin dictates what happens everywhere. Now, specifically the reason why we are looking at this is, remember, this is what we wanted to simplify. But if you look at this, del FB del theta 2C at theta 2 comma theta 1, essentially the same as this except for A and B being replaced by B and C. And then you have a contraction over A here. Here you have a contraction over the upper index of F, that is B. HAB evaluated exactly at F of theta 2 comma theta 1, where theta 2 is this. So this thing is nothing but the right hand side here, except for relabeling of the indices, of course. So this whole combination is nothing but HAC at theta beta at 2s minus 1. So now notice that U curly PS obeys exactly the same equation in this interval between s equal to half and 1 as U beta twice s minus 1 does. But that will not tell you that U curly PS is the same as U beta twice s minus 1. Simply because the initial conditions are different. At s equal to half, U curly PS is actually U alpha of 1. On the other hand, at s equal to half, U beta of twice s minus 1 is U beta at twice half minus 1. And that, of course, is not 0. That's, of course, wrong. That's U beta of 0, and that's nothing but the origin. So despite the fact that U curly PS and U beta twice s minus 1 obey the same differential equation, they are not the same first order differential equation. They are not the same functions simply because they don't obey the same initial condition. On the other hand, if you consider U curly PS U alpha inverse 1, note that U alpha inverse 1 is just a constant operator valued factor multiplying this thing from the right. It's constant, so it doesn't change the differential equation really, except for the fact that you have to be careful. You have to bring in this constant operator from the right simply because you cannot go across the operator TA. So U curly PS U alpha inverse 1 obeys exactly the same differential equation that U curly PS does. But at s equal to half, the value, of course, for this quantity is U curly P half times U alpha 1 inverse, and that's exactly the identity. The same initial condition as U beta twice s minus 1 at s equal to half. And therefore, what we can conclude is U curly PS U alpha 1 inverse is exactly equal to U beta at twice s minus 1. In particular, and this is why we are doing all this, when you come to the end of the path at s equal to 1, U curly P of 1 has to be equal to U beta of 1 times U alpha of 1. So it looks like we are done. We are at the point at the end of the path, theta p at 1, which is given by f of beta comma alpha. So if we do what we wanted to do all along, that is, if we identify U theta 1 with U of theta or U of t of theta, that is, if this becomes U of t of alpha vector and this is U of t of beta vector, then what we have just proven is that this result is the product of U of t of beta with U of t of alpha with no extra phase factor. So we do have apparently a non-projective representation. But there's a catch here. The catch is at the end of curly p, that is, if we move along theta curly p and get to s equal to 1, we have got to the point f of beta comma alpha. That's right. However, what we are not sure of is that have we really got to u of t of f of beta comma alpha, which is where we would want to be. After all, the question simply is this: is u curly p of 1 the same as u of f of beta comma alpha at 1? Remember, when you say u f of beta comma alpha at any s, you mean that you are going to solve our differential equation along the standard path which we laid down from the origin to the point f of beta comma alpha. We have not followed that path here. We have followed an entirely different path. And so the question really would be, is this result, the u of curly p at 1, dependent only on where you land up in parameter space, or does it depend also on the path? If u curly p1 is the same as u of f of beta comma alpha at 1, then we can identify u theta 1 with u t of theta and the non-projective transformation rule. U of t of theta bar, u of t of theta is u of t of theta bar, u of t of theta would work immediately, because remember, this thing t of theta bar, t of theta is nothing but t of f of theta bar comma theta, which is exactly what we hope this is going to be. The major question here is whether our final result is path dependent or not. If it is not, then we have completed our proof. The answer to that question of whether this result is path dependent or path independent involves algebraic topology, in the sense that it depends on the answer to the question: can we deform any two loops smoothly into each other while staying within the parameter space? Now, why this is so will require some more explorations into Lie algebra and the concept of simple connectivity. And that is what we are going to tackle in the next part of this lecture.